Okay, so now we've established the basics of that compound interest. Let's talk about going the other direction. Let's say that we think that we want to have $8,000 in 10 years. Let's say we're planning ahead to make a down payment on a house or something. And maybe we've got a large sum of money, whether it's inheritance or settlement or something. We've got a large sum of money right now. We want to know how much should we invest now at 7.3% compounded monthly in order to have that $8,000 in 10 years. Now in this case, if we look at our timeline, do we know how much money we have right now? No. We know how much money we want to have in the future. The $8,000 is in the future. That is a future value. We are trying to find the present value. So when we are going the other way, where we know what we want to have at the end, and we want to find how much we need to start with, the calculation goes a little bit backwards. The present value is the future value. Here's our big change. Divided by 1 plus our rate, divided by the number of periods in a year, to the power of our number of periods in a year times t, number of years. Okay, I'll pause to take a breath there. The point is, it's exactly the same formula. The only difference is, instead of present value times that factor, it's future value divided by that factor. So let's put in those numbers. We want $8,000. That's our future value. Divided by 1 plus 7.3% is 0.073. Compounded monthly, so divided by 12 to the power of 12 months in a year times 10 years is 120. Good. Give us $3,863.81. So $3,863.81 is what we need to start off with right now to have that much, the $8,000 in 10 years, if we invested at 7.3% compounded monthly. What do you think? Not terrible? Good deal.
I was very afraid at first.
Yeah? This is the baby formula to break us in for the big formulas next week. But if you understand this formula, the next formula next week is just this formula on steroids is all. So we're going to have you guys try a couple examples. Tim has so I brought it up. Yeah. Tim has $3,000 to invest at 6.8% compounded semi-annually for 30 years. Half a year, twice a year. Yeah. Semi-annually for 30 years. How much will Tim have at the end of 30 years? I'll give you guys a couple minutes to work on that. So first thing we need to figure out is which direction we're going. Do we know the present value or the future value? Present value is what we know. We want to find the future value. So we're going to take the future value is going to be the 3,000 times or divide? Times. 1 plus 0.068 divided by, careful, 2. Semi-annual is twice a year. You were thinking bi-monthly. To the power of, yeah, twice a year times 30 years is 60. So we have 3,000 times, parentheses, I got missing a 0, but I'll fix that later, plus 0.068 divided by 2, power of 60. So is that $22,302.50? Anybody have any questions on that one? Okay, next example. Pat invests $7,300. Whoops, sorry, not Pat invest. Yeah, why not? At 4.9% compounded monthly for 8 months. Find the balance at the end. I'll warn you, there's a little bit of a twist on this one.
I can finish writing it out right.
Yeah. Do we know the present value or the future value? We know the present value, $7,300. So we want the future value. So we start out with the 7,300 times or divide times 1 plus 0.049 and then compounded monthly means there are 12 periods in a year. So it's divided by 12 to the power of 8. because it's only 8 months. If you wanted to get technical to find that, there are 12 periods in a year. 8 months is 8/12ths of a year. 12 times 8/12ths is 8. So 7,300 times parentheses 1 plus 0.049 divided by 12 power of 8. 7541.90. So at the end of the 8 months, Pat will have $7,541.90. Any questions on that one?
So besides the
You get 7,300?
stock market, is there anything to actually invest in nowadays? Because I mean, these interest rates are awesome. What's actually out there isn't even like 1%.
Well, you're talking about going to a bank, though. To get better rates than that, you need to go to an actual investment planner. And yeah, you're not going to get 4.9% on 8 months. That's for sure. You'd be looking at tying up your money for a few years, and you're not getting it in a guaranteed CD. You're looking at probably like a corporate bond or something like that. I may have punched something in wrong. Let me try it again. I still get 7541.90. So let's punch it in together. 7300 times open parentheses 1 plus 0.049 divided by 12 close parentheses caret 8 something wasn't okay. We got her going now. That's what matters. Okay, let's say Chris wants to have $12,000 in 7 years to go to Europe. How much does Chris need to invest at 6.5% compounded monthly to reach that goal? I'll give you a couple minutes on this one. For this one, which one do we know, present or future? We know the future value. We want to have $12,000 in the future. So we want the present value. So we're looking at present value equals, what goes in here? 12,000 times or divide. Divided now, because we're going backwards. In the parentheses, we need to have 1 plus 0.065 divided by 12. In parentheses, 84. Again, yes, that is 12 periods per year times 7 years gives us the 84. $18,000. Oops, I did times instead of divide, didn't I? That won't work so well. Okay, let's do this again. There we go. 76, 22, 73. There we go. 8 questions on that one. So that is one of the toughest things to pick up on these, is that first step. Which one do we know? Do we know the value right now, or do we know the value sometime in the future? So you have to adjust your formula accordingly. Now this next part I'm going to show you, I show you kind of grudgingly because I don't care for it much. But there are tables for these. In your book, we're going to look on page 463 first. This is called the future value of $1 table. So if you look on that page, 463, future value of $1. Really, all this is going to do is, it's just another way of doing it. It's a simpler way of doing it. The problem is it only applies to certain problems. You look at the table here, and it's actually split up into 2 sections on that page. On the top section is 0.5% up through 5.5%, and the bottom is your 6 up to 12. There are 2 weaknesses here. One weakness you see is on the side, it has periods. This number here, periods, would be your n times your t. That's the number that goes in your power here. That would be this number right here, your number of periods. Well, you can see this only goes from 1 up to 30. So we can't go past 30 periods with this table. The other weakness is, you see the percents are only certain percents listed. So this is 1, 2, 3 on down to 30 here on the left. On top, these rates, you've got 0.5, you've got 1.00, 1.50, and so on. This would be the rate per period. That is actually a combination of these things here. Most of the examples we have done so far, we could not have done with this table. So let's look at an example that we could do with this table. Kim invests $4,000. Now this is the present value of $4,000. That dollar amount doesn't matter. This table does not. You can use any dollar amount in the table. We're going to do 6% compounded monthly for 2 years. We want to find the balance at the end of the 2 years. So the 2 things we need out of here: number of periods. How am I going to find that? Yeah, how many periods per year? There's 12 months. It's monthly, so 12 times 2 years is 24. That's my number of periods. So on the left side here, we'd find the number 24. My rate per period is going to be the 6% divided by how many periods in a year? 12. So that's 0.5%. So on top, we're looking at the 0.5%. We follow those down until they intersect, and we get 1.12716 is correct. What do we do with this factor? Well, the future value is equal to the present value times the factor when we use the table. So we're looking at 4,000 times 1.12716. $45.0864. So you're looking at that thinking that seems kind of simple. Why am I so against it? Why do I not like it? Well, because this number here only goes to 6 decimal places. It's a rounded number. Now for this one being a relatively short period of time, it probably won't be off by too far. But let's check it. This was with the table here. Let's check it with the formula. So 4,000 times 1 plus 0.06 divided by 12 to the power of 24. $45.0864. So it comes out to be exactly the same. So like I said, for this one, not going to be very far off. If we have higher percentage rates, higher rates per period, and we push up, well, this table only goes up to 30. In our old version of the textbook, it actually went up. We had from 30, then it did 60, 90, and 120 periods above that. Higher the percentage rate is, and the more periods there are, the further off these two numbers will be. At this point, these two are exactly the same, probably because it's a relatively low interest rate as well. But that's how that table in the book works. That's the future value table. In my math lab, many of the problems will ask you to do the table, and what you'll see is at the end of the problem, you see the problem listed out here. At the end of the problem, there's going to be like a little thing, almost looks like a calendar type icon. You click on that, it's going to pull up the table. So it'll pull up the table for you in my math lab. You can do them either way. If you like the table, go ahead and use it, but I warn you, the table can only be used on certain problems. And on the test that we're going to have in about 3 weeks, there will be problems that the table doesn't work on. So you do have to know the formula as well. In my math lab is pushing you to use the table. Most students usually prefer to use the formula anyway. So if you want to use the formula, go ahead. Just know that when it checks your answer, you might be a few cents off. On the homework, it doesn't matter. I will automatically give you credit for the homework. On a quiz, if it does that, let me know, and I will go through and I'll check them, and I'll give you back those points for the round outliers. Because to me, that answer from the formula, well, not to me. I mean, the answer from the formula is more exact than the answer from the table. The answer from the table is rounded. The next table that I want to draw attention to in the book is the present value of $1 table. And this is on page 477. Yes, I know I'm skipping over another table that is in there. We will come back to that. So this present value of a dollar table works exactly like the future value table we just saw. It's a little bit confusing because when we do the formulas, when we do present value, we have to divide instead of multiply. When we're using the table, the present value is equal to the future value times the factor. So when we're using the table, it's still times, because they take that division into account when they create the factor. So that's already part of the factor. So let's take a look at a present value problem here. And let's say that Peyton invests, or sorry, Peyton invests. Peyton wants $4,000 in 5 years for a car. How much should Peyton invest at 4.9%? I can't do 4.9%, so let's go 6% compounded quarterly. So, first thing we need to find. Number of periods. How many periods in a year? Compounded quarterly. Did I say compounded quarterly, sorry. So 4 times per year times 5 years is 20 periods. The little hamster must be way off the wheel tonight, I'm sorry. Next, we need to find the rate per period. How are we going to do that? %6 divided by how many periods are in a year again? 4. Good. 4 periods a year because it's quarterly. That's 1.5%. So in the mighty table, we go to 20 periods over here, 1.5% up here. We find a factor of 74247. So our present value is equal to the $4,000 future value times 0.74247. So 2969.88. So $2,969.88. Now, just for fun, let's check that against the formula. See what the formula would have come up with. Present value is our future value of 4,000. Now, since it's the formula, we're going to divide by 1 plus 0.06 divided by 4 to the power of 20. $2969.88. So I'm not making a real strong argument that the table is not as accurate as the formula here. Now, I could come up with examples that would work, but they'd seem really contrived. So if I were to get up to like, the 6 or 7% and up to about 30 periods, there would be a big difference. Okay, so there was a third table in there that we flipped past. This third table is on page 472. If you look at the top of this table is labeled compound interest on not $1 but $100 compounded daily. Now it also says exact interest 365 days, blah, 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 blah. That's just saying they're using exact interest rather than ordinary interest, because it's an investment instead of a loan. For a while, some banks were using something called continuously compounded interest, which meant that every moment of every day the interest was added to your account and the balance went up. With computers, it's not that bad. I'm even doing it by hand. It isn't a horrible formula to do, but it involves the natural constant E. So we're not going to get into that here. But compounded daily is literally at the end of every day, the interest is calculated and added to your account. This table, however, is not friendly or fun to use. Let's take a look. Let's say Kim invests.
Tell me on these,
Go ahead.
on these tables, why are some of them highlighted in blue? I mean, like some big sections.
Well, one is some of them that are highlighted in blue are for examples that are used in the book. Some of the lines in blue are just to help you follow the lines without jumping a line.
Okay.
So Kim invests $8,000 at 8% compounded daily for, now notice the time on the left side is in days. So let's say for 180 days. Find the future value, the ending balance. I'm going to pause, make sure everybody's got this written down before we start, because this process is not as simple as the other tables. The first thing you'll notice, this says compound interest on $100. What that means is we take the amount invested, the 8,000, we have to figure out how many hundreds are in it. That means we divide it by 100. So that's the first step when dealing with this daily compounding table, is you have to divide the present value by 100. So we get 80. So that's what we're going to be using for this calculation, is 80. Now in the table, we find the 8% on top and the 180 days on the side, and we get a factor of 4.023613. Everybody find it? So we are going to take this $80 times 4.023613. $321.89. Is that my answer? So I would hope not, because that's less than the 8,000 they put in, right? If you look at the title of this table, the other table said future value of $1 or present value of $1. This one just says compound interest. So what we just found there is the amount of the interest. To find the future value, we need to take the present value of $8,000 and add the $321.89 to it. So that future value, the ending value, is going to be $8,321.89. So as you can see, that table is a real pain to use. Can we do this with the formula? Well, geez, I'm glad you asked, because yes, we can. Okay, 8,000 times 1 plus 0.08 divided by 365 to the power of 180. Let's see what comes out of that. $8,321.89. Any questions on whether I got any of the numbers in this formula here? Okay. If you ever notice, there are certain problems where I'll always do the interest in one color and whatever. So yeah, there is a pattern to some of it.
We're working on that, but we can't keep up with exactly what colors you're going to use.
Oh, sure. Are you trying to guess what color I'm going to use next?
Well, no, we're trying to make sure, because it makes more sense to us to see it on paper the way it is.
With colors? Sure.
So we are trying to match it up so that we picture it.
Sure. Okay. Like I said, when it comes to doing my math lab, I'm going to leave it up to you guys whether you use the table or use the formula. But you will have to know how to use the formula because there are some problems that just plain will not fit into the table. So let's do some examples here to take us up to our break. Let's say Pat invests $7,800 at 3.4% compounded monthly for 22 years. Find the balance at the end. I'll give you a minute to do that one. So looking back at this problem, first thing we got to figure out, we got the $7,800. Is that a present value or future value? Present. So we know the present value. We want the future value. So the future value equals what? 7,800 and then times and then parentheses 1 plus 0.034 and then It is compounded monthly, so divide by 12. To the power of 12 times 22 is 264. $16,462.19. How many of you had that one correct? Okay. Any questions on how I got that? Anybody want me to go back through any part of that? Okay. Eddie needs $2,100 in 4 years. How much should Eddie invest at 5.1% compounded compounded quarterly to reach this goal? I'll give you a minute to do that one. So we have the 2,100. Present value or future value? That is in the future. Eddie needs $2,100 in 4 years. So that's going to be at the end of the 4 years. So we want to know how much we need now. So we are calculating a present value. That equals our $2,100. What's next? Divided by. Good, because we're going backwards. Parentheses. 1 plus 0.051. Compounded quarterly, so divided by 4. The power of 16. Good. 4 periods per year times 4 years makes 16. So 2,100 divided by 1 plus 0.051 divided by 4, power of 16. 1,714.68. How many of you got that one? Okay, a few less. Any questions on how we got there? Everybody sees where the mistake was? Okay. It is time for our second break, but I'm going to put a problem up here to kind of think about over break. And this is what we're going to start off with at 7:30 when we come back. Kim invests $7,300 at 5.25% compounded daily for 2 years. Find the ending balance. So we are going to take our break. We're going to come back at 7:30, but I have that up there for you to think about